The next step are these algorithms. Now, the reality is, yeah, they again have more complex names and stuff like that, but the key is, how do you think about data and what do you want to accomplish? One of the things, Sandeep, you talked about, you and I were talking about earlier, is how, yes, there's these algorithms that are out there, but really that's not the point. The point is that we need to create new algorithms to solve some of these problems rather than just relying on the existing ones. Can you walk us through a little bit more, like, how do we think about this, or are we stuck with what we've got here?
No, I think these are some of the algorithms that the world has sort of thought about well before quantum computing became a thing, right? So if you think about Grover's algorithm, or in fact Deutch-Jozsa, which you're trying to understand balance sets and things like that, it's a problem that we've had for a long time. But fundamentally, the way we've articulated it is in the language of classical computing, right? So think of, hey, if all you know is English, you're going to talk about a problem in English, right? But now suddenly we have this new language where instead of going between 1 and 0 or 0 and 1, now suddenly you can go into multiple states between 0 and 1, right? So I think a lot of algorithms have to come in which can utilize the power of those things and not just think about in a very sort of 0 and 1 way, for example, right? Another one to also think about is, because in quantum computing, yes, there can be many states between 0 and 1, but fundamentally, when you try to observe something, it's going to have to be either a 0 or a 1, right? So which means that you may get an answer which is not the most appropriate answer the first time. So you may need to do the algorithm a couple of different times to know what's the most likely answer, and that still will be faster than classical computing, right? So right there, how many times do you run this algorithm to know that you actually arrived at the right solution, right? A very simple problem, but again, an algorithm had to be found out, and how do you do it? What's the fastest way to do it? And things like that. So again, it's a new language. Formulating the problem in the old language doesn't really help. So in some ways, that's where the algorithms need to evolve.
Perfect. So one of the things that we're going to highlight a little bit is Shor's algorithm. And yeah, we're not going to go into the details of the math behind this, but can you walk us through one of the most exciting algorithms? It's an older algorithm. It's been around for decades. But what's so exciting about Shor's algorithm, and why is it one of the big things that everybody, including the NSA, is very excited about?
Right, and so this is sort of the foundational algorithm behind cryptography today, right? So it's the idea that you can take two large prime numbers, very large prime numbers, multiply them to get to a number, but that's easy to do, whereas what is really hard is to take the answer and figure out what the prime factors are, right? That's something very, very hard, and that's important for cryptography, because then think of those two prime factors as the keys to the encryption, and if you don't have the keys, you can't decrypt the data, right? So fundamentally, our entire cryptography is dependent upon the fact that it's very hard to factor prime numbers. Now, it's hard not because the algorithm hasn't been there. Algorithm is the Shor's algorithms, and it uses sort of the mod operator to figure out how do you best arrive at the prime factors for any different number. But the problem is, as the number becomes bigger and bigger and bigger, it takes incredibly long periods of time to do this, right? And again, this is because a classical computer will need to solve it in a brute force approach. It takes this algorithm and then it keeps running and running and running until you get an answer. But now suddenly think about qubits, which can take a lot of different states between 2 and 1. And it's the same drone versus the Himalayan Sherpa analogy, right? You can start at so many places, which means you can exponentially speed up the execution of this algorithm, which means theoretically you can break the encryption very, very quickly. So today the RSA encryption relies on a certain number of digits. That could be relatively easily broken with something like this. Again, the algorithm is there, but how you execute it, how quickly you're able to do that, that's what's preventing us from all our data being leaked. And with quantum computing, that becomes a possibility that you can break into.
So that's why it's also exciting on the flip side, which is everything's always going to be an arms race, in the sense of, like, that's why you go from 128-bit encryption to 256 to 512 to et cetera. That there's always going to be something that's going to be more powerful. And again, don't get too hung up on the architecture and the technology itself. Once quantum computing becomes general purpose, which it's building the framework there right now, you'll be able to decrypt quantum encryption. as well. So you'll be able to have the same experience, and we're going to talk about that in applications in a minute, but you'll literally be able to have, like we talked about, a quantum computer in your pocket because you can access it remotely, and everybody will be able to have that same level of security. So all the people are freaking out about how every password in the world is going to be broken. Sure, but that's of today's passwords relative to tomorrow's passwords. They're going to be able to use both sides of both the encryption and the decryption of a quantum computer.